Today, we're going to dive into a paper from 1970 by a guy named Burton H. Bloom. Now, it might look pretty old and academic, but trust me, it introduced a brilliant trade-off between space and time that is absolutely essential for the high-speed apps we all use every single day. Okay, so think about this. You're signing up for a news service. You type in a username you want. How in the world does it check against a database of millions, maybe billions of other names almost instantly? It doesn't feel like it's grinding through some massive list, right? It's just immediate.
Well, believe it or not, the secret sauce, or at least the start of it, comes from right here. This paper, from over 50 years ago. It tackles this exact problem. How do you check if something is part of a massive set without bringing everything to a screeching halt?
So to really get why Bloom's idea was such a breakthrough, we have to first look at how things used to be done and the fundamental problem that the old way always ran into.
The old school way was, pretty straightforward. You create this big digital filing cabinet called a hash area. For every single username, you generate a unique address, a hash, and you just store the entire username right there. If you need to check for it later, you just go to that specific address and see if it's there. Simple enough.
But, and this is a big but, to guarantee you're 100% accurate, that filing cabinet, that hash area, has to be absolutely massive. So big, in fact, that it often won't fit in the computer's fast, easy-to-reach memory. It has to get pushed off onto something much slower, like a disk. And that just kills your speed. So you're stuck, right? You've got this choice. The conventional method is perfectly accurate, but it's a space hog, which makes it slow. Bloom's new idea promised a tiny memory footprint, but what's the catch? What's the price you have to pay for that incredible efficiency? And this is where things get really interesting. This is the core insight of the paper, a totally counterintuitive idea that just flips the whole problem on its head.
Let's hear it straight from the source. Bloom himself said, what if we allow a small number of errors? What if we're okay with the system sometimes falsely identifying an item as a member of the set? If we accept that, he argued, we can use a much, much smaller hash area. The key here is that phrase, allowable errors.
Now, the system is designed to only make one specific kind of mistake, a false positive. It might tell you a username is taken when it's actually free, but, and this part is absolutely critical, it will never have a false negative. It will never tell you a username is available when someone already has it. So how on earth is that possible? How can you check for something without actually storing the thing itself? Well, this is where the paper's method 2, which is basically the granddaddy as what we now call a Bloom filter, comes into play. The big idea is to stop storing the data. You heard me right. Instead of storing the actual username, for every name you add, you just leave behind a few little digital marks, like fingerprints, in a shared space to prove it was there. Okay, here's how it works. Imagine you've got this long strip of light switches, and they're all in the off position, all set to 0. Now, let's say you want to add the username explainer. You run it through a few different secret formulas, hash functions, and they spit out, say, 3 different locations on your light switch panel. You just go to those 3 switches and flip them to on, from a 0 to a 1, and that's it. The word explainer itself is never actually stored. So what about checking a name? Someone else tries to register explainer. We run it through the same 3 secret formulas, get the same 3 locations, and we go check those light switches. If all 3 are on, we say, that name is probably taken. But what if someone tries a totally new name, like podcast? We run it through the formulas, check its switches, and what if one of them is still off? Boom! We know with 100% certainty that name has never been added before. It is definitely not in our set.
And this isn't just me making up an analogy. If you look right here in the original paper, this is exactly what Bloom was describing. He said it completely gets away from the conventional concept by using a shared space and just setting a few distinct bits to 1. It's the same elegant idea.
Okay, so we've accepted this tiny chance of being wrong. So what do we get in return? Well, this is the aha moment. This is where the payoff for this whole trade-off becomes crystal clear. I mean, this is the million-dollar question, isn't it? Is this clever trick just a small optimization, or is it a real game changer? How big is the reward for being good enough? This graph from the paper tells the whole story. Seriously, just look at it. The vertical line is how much space you need. The top curve, that's the old, clunky way. And that bottom curve, labeled method 2, that's Bloom's idea. I mean, it's not even a fair fight. It is just wildly more efficient.
The result is just incredible. By being okay with a tiny chance of a false positive, you don't just save a little memory. The space you need just plummets. It shrinks exponentially. You're trading a little bit of certainty for a massive gain in efficiency. And we're talking about real numbers here. Look at this data from one of the paper's examples. If you're willing to accept a 1 in 8 chance of error, you save almost 79% of those slow, painful disk lookups. With just a 1 in 32 chance, you save over 87%. That is a huge, tangible performance boost. All right, let's bring this all together and talk about why this 50-year-old idea about the power of probably is more important now than it has ever been. The original example in the paper was for a program that hyphenated words. Kind of quaint, right? Most words followed simple rules, but about 10% of them had to be looked up in a huge dictionary stored on a really slow disk. By using this method, the program could first check a tiny in-memory filter to see if a word was probably in that special dictionary, avoiding that slow disk lookup almost all of the time. And the results were just stunning. In that one example, with an error rate of about 6%, the new method reduced the required storage space from 2 million bits down to less than 300,000. That's a reduction of over 85%. That's the difference between an idea being practical and being completely impossible. So here it is, the main takeaway from all of this. The core principle is making a smart trade, giving up a tiny, acceptable bit of certainty to gain an enormous amount of speed and efficiency. Today, this idea, which we now call a Bloom filter, is used everywhere, from databases preventing unnecessary disk reads to web browsers checking for malicious websites. And this really leaves us with a fascinating thought. We often think of computers as being all about 100% precision all the time. But as this paper showed us so long ago, sometimes the most powerful, the most elegant solutions are the ones that understand the incredible power of just being good enough.